What?
What about our questions? Our questions. How can
What about what?
uh, what about our questions?
Your questions?
Question. Yes.
If you have any questions, you can ask me in here or even in WhatsApp. You can, because I think you can easily work with WhatsApp. It's easier, yes?
WhatsApp is
Yes, okay. If you can, even if you can use Skype, I think Skype is even better than here. Okay, you can use Skype.
So for now, if you want, you can take class. My connection is okay for now. I can take notes and send them.
Okay, okay. You can anyway. You can ask your friends if they can make it with Skype or even Zoom or any other application, so we can use the other one because I think this one is a little uh, heavy for your connection.
I have Skype. I don't know the others.
Okay. I don't know. Ways I'll try Skype or Rafa try Skype. If it's better, we can move to Skype. But for now, I'll record the file and upload it again, so you can have it forever, not just for the bench day.
Okay.
What was the last thing? Do you remember? For steel design. Do you remember that, Shadla? What was the last thing?
I don't know.
The last lesson, teacher.
Uh-huh. Yes. Okay.
The last lesson, the brittle material, ductile material, also
Got it.
brittle
Understood.
materials.
Got it. Understood. Okay. So, let me check if it's recording. Okay, it's recording and you can see my screen. Okay, from now on, you have to use two books. One of them is a textbook, steel design, that I'm teaching. The other one is the specification. Specification is AISC. Okay. AISC. American Institute Construction. So this AISC 360. This is the book that I'll upload it. We can see it here, AISC 360. And in this book, we have different chapters. You know, in steel construction or steel design, we have. Wait. Okay, in steel construction or steel design, we have to use equations and relationships that it's not easy to drive. So I'm not going to ask you where does this, for example, equation come from. Okay, you just should use this. let's go to chapter B. This book has different chapters. Chapter A, B, C, D, whatever. We start with chapter D. Okay, we start with chapter D. So uh, this chapter is for design of the members under tension. Okay, what does it mean? If you remember from your different classes, we have different types of loading. One of them is, for example, tension. The other one is compression. The other one is flexure. Or bending. The other one is shear. Depends on the loading. For example, you have a member like this. Uh, it's in this case, this member is under tension with the load T. Okay. In this case, for example, if we have a member like this force, in this case, the member is under pressure. If we have, for example, the other case like this, for example, a beam, you have, you know, these different cases from structural engineering or from strength of material. Just I'm going to review it. For example, if we have this type of loading, this is shear, this is compression, and this is tension. Mainly, we show tension with T, compression with P, shear with V, and bending, the other type, mainly in beams, is moment. Bending is moment, like this, with M. Okay. So if I ask you to design a member, if you ask you to design a steel member, first of all, you should know that what are the loads acting on this member. For example, in this building, for example, this is two-story building. You want to design this. Okay. In this building, we have different members. Okay. They are beams. They are columns. These are uh, braces. So if we have different types of load, for example, dead load, I talked about them, dead load, live load, and their factors. I think we talked about it, yes, about dead load, live load. For example, one of them is 1.D plus 1.6 L. We have different loads acting. So depends on these loads, we have different responses in these members. For example, if we have these loads, braces are under tension. Okay, we use braces like this red one, to resist against uh, lateral loads. For example, earthquake, wind, they are lateral loads. They're acting from the sides, not from up or down. So we can resist against these loads. I'm just going to give you the whole idea about these parts. So, for example, I can tell you that we have, for example, braces, X brace, or let me see if I can show you the braces. For example, look at here, they are brace. Can you see it? Here, they are braces. Okay. Uh, the other types here, you can see that they are steel braces. We use them to resist lateral loads, and because of their type, they're mainly under tension. Okay, they're mainly under tension. When we want to design a member under tension, you have to first. This book explains the whole phenomenon, the whole concept in detail. So if you want to uh, learn more about this type, you can read this book. But mainly, if you want to design anything in future, you have to use this book. It's AAC. Why? Because here it says that when you want to design, you have to this formula. You have to use the other factors. Okay, effective area. So here you can have all the information, uh, or you can have a summary of all the information because it's summarized. Anyway, so let's talk about the designing of tension or members under tension. We have when in all the cases, not just for tension, for compression, for flexure, for shear, in all cases we have different failure criteria. What does it mean? It means, for example, I showed you, I think, for example, let me show you. I have a project right now. I can show you this. For example, this one. This is a member. For example, here you can see that this is the force, and this is a member, a steel member, and look at the direction of this load. It's like this. We have a member like this, under tension. Okay, this is tension. We'll see that if we increase the load, what's gonna happen? Look at here. This is the failure. We'll have rupture in here. Let me show you. At first, you can see that. If you remember, I told you about necking. Okay. At this part, if you focus, you can see that we have necking in here. One of the failures so far is necking or yielding in the other word. And if we increase the load, what's going to happen? Failure. You can see that we'll have failure and finally rupture. Okay, you'll see that this is the rupture. So if I ask you what are the failure criteria in tension, you can say that one of them is yielding. The other one is rupture. Okay, so if you want to design something, if you want to design something, uh, you can, you have, not you can, you must check if the member is resist against these failures. So it's obvious when you need a member, you're not gonna you shouldn't let this member fail. Okay, so in this case, look at here. In this part, this member is not useful. You can't use it. It's not functional. If you have a rupture in your member, you can't use it anymore. For example, suppose that in your structure, look at here, for example, suppose that you have a rupture in here, for example. So it's not functional, and the structure will collapse. Suppose that you have, for example, a failure here, a failure here. So these failures, uh, these failures affect your structure, the capability and the ability of your structure. So you have to avoid, uh, you have to prevent from these failures. How? By following some instructions. Okay. A rupture is obvious. Rupture is obvious. I showed you. Uh, I already showed you. This is the rupture. Okay. But what about yielding? If you remember, I talked about. If you remember, I talked about the behavior of steel. For example, like this. Okay. This is a stress, and this is a strain. If you remember, I told you that this part is elastic and this part is plastic. The maximum capacity in the elastic part was what was this Fy, or yielding, F yield, stress at yield. One of the other things, I told you that in here it's plastic. The behavior in here is plastic. So it's not an acceptable in many cases, not in all, but in many cases, if you be in this part, it is not acceptable. So you should avoid being this part, being in this part. So the other part, or the other criteria that you have to uh, prevent from happening, is yielding. So far you have to check yielding and rupture. Okay. The other thing that you have to check at the end is slenderness. Slenderness. Do you know what does it mean, slender? Slender, for example, this is a member in this dimension. For example, the length of 2 meter and the cross section of 1 meter in 1. Okay, you can easily see that these dimensions are somehow consistent. What does it mean? That means the cross section is 1 meter and the height is 2 meter. But what if, for example, we have cross section of 1 centimeter and a length of, for example, 10 meter? Okay, the cross section, it works like a needle, like a needle. Okay, so in construction, you are not allowed to use what or any dimensions that you want. So the dimensions should be consistent, as I said. Or in the other cases, for example, suppose that you are using a column like this. For example, 4 meter in 4 meter in 3 meter. Okay, this one is not economic. You can't use this. You're wasting your money. You're wasting the material. So you have to uh, make a balance between uh, you have to make a balance between every dimension. Okay, So far I talked about the criteria, failure criteria. So how can we check if all these criteria? Here you can see that from the beginning. It says in here we have to check. The first one is slenderness, and the second one is yielding, and the last one is rupture. So in this chapter, you just need to check these three criteria. So let me summarize it again. For example, I'm asking you to design a member like this. For example, this is a beam. Okay, this is a beam. If you remember, because of the shape, it is called what? I section. Why I section? Because this section is like letter I. Okay. This member has different properties. One of the properties of this member is its length, L. The other one is its cross section. Cross section is like this. Okay, the cross section is like this. I section. This section has different properties again. One of the the most important property is what? Area. The most important thing is area, and we show it with A. The other thing is this one. We show it with B. H, T, with TW, and TF. Okay, TW, TF. What are they? We call this, or we can show it with BF even. If you remember, we call this flange. Okay, flange. This one is called web. Okay, so it's obvious. What is TW? The thickness of the web. What is this? Thickness of the flange. This is the area of the member. And BF is the width of the flange. H is height of the member. So if you know these parameters, you'll know everything. Okay. From the strength of material, you know that stress is equal to force divided by area. Okay, force divided by area. Charlotte, how is the quality? You can hear me well? You hear me or not? Elchin.
Sorry. Yes, teacher.
Okay. Um, okay. I've been talking about. I was talking about this one. Stress is equal to force divided by area. So if I want to find the final force, what would be the final force? Force is equal to stress dot area. Okay, force dot area. So in here, for example, in this section, if I tell you that the cross-section area is A, for example, area is equal to, for example, 25 centimeters square. Okay, the cross-section area is 25 centimeters square, and as based on our test like this, I told you that this is Fy and this is Fu. If I tell you that this is 40 megapascal and this one is 255 megapascal, if I ask you force, what is the force at yielding? To find the force at a yield point, all you need to do is that you know that Fy, as I said, Fy is stress at yield point. Okay, and it is given here.
Sir, I'm sorry. Can you repeat the last part?
Which one? Yield part?
Şey, yes.
This one? This curve? Okay. Uh, I told you that, for example, in experiment we have such thing. Okay. This is a steel member. Okay. We perform test on samples like this. Okay. To find its behavior. To find its behavior. For example, I performed a test on this sample. For example, in before when I was a student, I performed a test on this sample. And this is the answer of the test. You can see that this is the real behavior of this test. So after this test, you'll see that at this point, before that, you can see that in here, let me zoom it, we have a straight line. It's completely linear. Okay. But at this point, we have something, then we have nonlinear and plastic behavior that I talked. At this point, you can see that we have the maximum capacity and then the capacity reduces to 0. Okay, this is the real behavior of steel. So I have this sample and perform a test on this, and as I showed you, for example, this is the test. Finally, we have whatever. Finally, we have this. Okay, this is the failure, rupture failure. After performing this test, we'll get this one. In this case, let me show you. In here, this is what F, or let me write it in this way. In here, we have yield. What was the yield? The yield point is a point that before that we have linear behavior, linear and elastic behavior. After that, we have elastic behavior. So you can see that From here, after this point, we have plastic behavior. Before that, we have elastic. And this is the maximum or the maximum point. What is this? This is ultimate. But suppose that you are constructing a huge building. Okay, for example, you are constructing a building, for example, 100-story building. Okay, like a tower. You can't test it because to see if it works or not. Okay, to make it easier, you test a small sample like this, for example, like concrete technology. If you remember, I told you that, for example, we have samples, cubic samples or cylindrical samples. We check the capacity of the concrete with these samples, and when we find the capacity, for example, F prime C, we use it in our calculation. We can't test a huge column in the building, a huge concrete column. So instead of this, we test small samples, and when we get the information like this or like this, we'll use these information instead of, for example, testing a huge building, and they're accurate. So at this point, we have ultimate capacity, and we show it with FU. U stands for ultimate. At this point, we have Fy. Okay, sorry, this is F. This is Fu, not capital F. So this point is yielding, and this point is ultimate. So by performing tests, we'll have this behavior. And when we get this one, we can design and check our structure. How? Like this. As I said, we have three probable failures. As I said, one of them is yielding, like this. Because, for example, if you are designing, for example, except for example, a huge earthquake. Okay, for example, I'm not talking about, for example, a huge earthquake. I'm talking about, for example, your load when you are in your home, for example, or when you are in your classroom, or when you are in kitchen, or wherever. When you are in that level of performance, you are not allowed to be in here. This one is not permitted. Okay, when you are using or when you are an ordinary performance, all you allow is here. So yielding is one of our failures. The second one is rupture that I talked, and the first one that I told you is slenderness. I told you that it's not reasonable to use this member for your structure. For example, you are when you are making, so for example, fences for your yard. For example, to prevent animals from getting inside. Okay, you are allowed to use this section. But when you are when you are building structures, you're not allowed to use them. So the other thing that you have to use is slenderness. You have to check is slenderness. The other one is yielding, and the last one is rupture. Okay. Suppose that I gave you, for example, these information. One of them is uh, area. For example, I gave you all the geometry of this member of this section. Area, uh, length, What else? For the test, Fy, Fu, and I ask you to find tensile capacity. What is tensile capacity? In not just in tensile, in tension, in all the this is the process. Okay, this is the process in all chapters. First of all, make your failure criteria. Okay. The second step, find the capacity for each criterion. Three, the final capacity is the minimum amount among all of criteria. Oh, at the first step, the main criteria, as I said, the first criteria is yielding. Second one is rupture. And the last one was slenderness ratio. Okay. If you want to check the yielding capacity of a member, you have to follow this equation. Look at here. For tensile yielding, you have to use uh, this equation D21. Okay. Equation D21 says that the final capacity, Tn, for example, for yielding for Tn1, or let me write it in T, is equal to Ag dot Fy. What's this? I told you. Let me find it. Force is equal to stress dot area. But what is stress? What area? Ag and Fy. What is Ag? For example, let me see if I can find something for you. Uh, for example, like here. Hmm, like this. Okay. This is a connection, and here we have a member. Or like this. Here, for example, this is, if you remember, this is a U channel member. This is a U channel. If you see, we have a couple of bolts here. like here. And but in this part, we have nothing. Okay. When we want to find the capacity, we have to know that which area we should use. For example, this cross-section area or this cross-section area that we have a couple of holes. You can see that we have holes here. Yes, we have holes here. So if in these cases the whole area like this without considering any holes, okay, we may have a couple of holes here, okay, we may have a couple of holes here, but we have nothing here, okay. The area without considering any holes is called gross area, and we show it with AG. G stands for gross. So in here, in this book, it says that if you want to find the tensile yielding capacity, you should follow this equation. For example, in here we have, in our case, AG, for example, is 25 centimeters square. Fy is 255 megapascal. What is the total tensile capacity? 25 dot 255. This is for yielding. In future, for example, the answer is 10 ton. Okay, I'm not sure, just an example. Okay, for example, for this one, where is the criteria? For this one, we got 10 ton. For this one, we got 12 ton. For example, for this one, we can pass this one. What is the total capacity? I told you that you have to take the minimum. Okay, we have to take the minimum. So the minimum is 10 ton. Your final capacity is 10 ton. Okay. The final capacity is 10 ton. I have to say something, and we'll continue our class for next time. So far, I talked about AG, gross cross section. But we have another thing. AE and AN. This is effective, and this is net. This one is gross. Okay. Gross cross section. I already told you what is gross. Let me see if I can find any better. Okay, YouTube is not working here. And I'm using VPN as well.
Why?
It's filtered here. Okay. Let me see if I can show you. Okay. Uh, for example, this shape. Okay. For example, this shape.
We can see your screen.
Okay, if it's okay, so I write it here. So, for example, you have this section and you have a hole inside this section. Okay. Suppose that the dimension of this is, for example, 10 centimeter, that's 2 centimeter. And the diameter
Sir,
of
you
this,
didn't share your screen.
okay. Ah, you said it can't? I thought you said it can. Can you now? Can you see it?
Yes.
Okay. Dimensions. Can you see my screen? Hello or not?
No.
Yes.
Yes or no? You can
No.
see it. Maybe the problem is.
Sen ne görsen şöyle ben ne görsen.
Yo, məndə görsənmir. Getdi.
Okay.
Hmm.
Right now, suppose that this is a plate. As I said, we have a hole inside. Okay, this is a hole. The dimensions are like this. If I ask you to find AG, what is AG? This is the cross section. This is the force, and the cross section is the area perpendicular to the force. Okay, Shala, what is AG? The cross section of this hashed part, this part.
Mhm.
What is
Gross
what,
area.
2.10?
10.
2.10. This is the cross section. But if I ask you, suppose that this is a hole with a diameter of 2. Okay. If I ask you to find, I'm gonna add a section cut here. What would you see if I add a section cut? The thing that you see that is something like this. Yes?
Yes.
Okay. So if I ask you to find an area here, the area is here, like in this section, the area is this. So what is the area? What is the red, the highlighted area? The highlighted area is 2 dot. It was 10, and this one was 2. 2 dot 10 minus what? Minus this part. Okay. What is this part? 2 dot 2. We call this red part.
Teacher,
What? We call this net area. We call this net area. Robert, is it clear?
Why 2.2?
Thickness is 2. Okay. This part is obvious. But this is the missed or the lost part. This is the diameter of the hole. If, for example, here you have something, here you don't have anything, but here you have it. So what is this? I'm look from the top. The total is 10 minus this 2. Okay, you can see it here. Look at here. This part doesn't count like this. So this is,
let's see your screen.
you can't or you can. I'm recording it and I'll upload it again so you can have a look.
Veysel sen de internet TRT başarılı ona göre biraz cihaz atır sen de.
Okay. For example, in this case, this is a connection. We call this one gusset plate and this one a plate. For example, in here, it says that the plate dimension is 1/2.5. What does it mean? That means the thickness. It says that. It says the thickness is, the plate is like this. I'm gonna show it in 3D. This is the plate, like this. The thickness is 1/2. The smaller one is the thickness, 0.5 or 1/2, and the width is 5. Can you see this symbol? It means it's a lined plate, so the length doesn't matter. Okay, so if I ask you what is the gross cross section, you can say that the gross cross section is 0.5.5. So AG is 0.5 or 1/2.5 inch square. In here we have uh, two holes. For example, if I ask you what is the cross section here, if I ask you what's the cross section here, you can't say, if I ask you what is the net cross section, you can't say 2.5 anymore. Why? Because we have two holes. They are holes. They're not there. There is nothing inside. So it says that the diameter is 5/8. Okay, the diameter is 5/8. Now I'm gonna ask. Okay, Robert, can you answer this? For example, this is your plate.
Okay. Yes.
This is your plate, and you have two holes like this. Okay. The thickness is 0.5, and the diameter of each hole is 1 inches. Okay. Answer, what is AG and what is AN or net? Can you answer this?
Okay. AG is 5.0.5.
AN,
And it means 5.0.5 minus is 1 inches.
5 minus 1 hole, 2 holes.
1 divided by 2.
1 minus 1. 5 minus 1 minus 1 dot 0.5. Or
And 2 whole. It means that 1 minus 1.
no, I mean this is the area.
Okay.
What is this length? The red line. Can you tell me what is the length of this red line?
3.
The red line.
Yes, 5 minus 1 minus 1. And the thickness is 0.5. So this is your net area. Okay.
We're not gonna consider that holes as a circle, yes?
No, yes. You know why? Because if you look at it at this part, you're not gonna see a hole. Look at here, you'll see a rectangle. Can you see it? Can you imagine it? That's why we consider it as a rectangle. Okay, that's enough for today. Try to join for the next class, seismology. Okay. See you for now.